on here. And so if I put another 200, I might actually hit the table here. Why don't I move it forward here so I can go below the table. But if I pull that down, it'll start oscillating. And it takes a long time for one cycle. And so you can see in the equation that mass is part of it. And hopefully it's not a big surprise, because we learned way back in our first chapters on mechanics that mass is a measure of its inertia. It's a measurement of its resist to change its motion. See, that spring has to make it go down and stop and then snap it back up and then stop it and push it back down and stop it. And so it's constantly changing the motion of it. And so the spring then is going to have a harder time doing that. In other words, it's going to take more time to do that if it's got more mass. And so the fact that more mass takes more of a period hopefully is not a surprise. And that's what you see here in this equation. And so the equation simply says, look, more mass would give you more period. Now, I would say something that is not quite so obvious till you go through the derivation of this is that it's the square root of the mass. See, the reason I put 400 grams on here was to kind of show you that if I start with 100 grams, so here's 100 grams and I let it go, that has a certain period. Could I increase the period? Well, yeah, more mass, right? Give it more inertia. That resists its change of motion. All right, but let me ask you this. How much more mass would I give it in order to make its period twice as long? And notice it's not twice the mass, right? Do you see that in the equation here? It's a square root. And so right here, in order for this whole equation to increase by a factor of 2, I have to have a factor of 4 inside of the square root, right? Because the square root of 4 is 2. So I could double the period if I quadruple the mass. That's what I'm trying to point out here in this mathematics here. So looking at this going up and down, I could double its period if I quadruple its mass. And so that's why 2 200s, which is 4 times the 100 that was on there, is 4 times the mass, and this then takes twice as long, or roughly twice as long. I say roughly because we also had the mass of the spring, and so we just doubled the mass we were hanging. We didn't, quadrupled the mass we were hanging. We didn't quadruple all the mass. But within reason, we quadrupled this mass. And when we quadruple it, then the square root of that 4 makes double the period. And of these two, that's kind of the easy one. The harder one to comprehend, where I want to spend a little time here, is this spring constant. What is that? Well, we call it a spring constant because it's related to the spring, and it is a constant. But what do we mean by it's related to the spring? Well, it's really a measure of how stiff the spring is, how much it pulls back. We like to define it this way. The spring constant is a number of the force, maybe I should spell that out, versus the length that I pull it. In other words, if I come over to here, and let me just take the masses off. And let me make sure this is good and hooked here. By itself, the spring is about this long. So if I were to grab it, and I'll just pull it kind of horizontally and down, and stretch it, and I'll go about 1 meter. So I stretch it 1 meter. How much force does it take for me to stretch it 1 meter? Now, if I were to stretch it 2 meters, that would take twice as much force. But notice then the ratio of the force to how much length it stretches is the same number. It is a constant. And so that's why we refer to this then as its constant. It stays the same. And in fact, this was discovered by a scientist named Hooke. So we call this Hooke's law. He noticed that, again, if you were to pull it, and this one I happen to know just because I've measured it so many times, it takes me about 9 newtons to pull it 1 meter. Or it takes me 18 newtons to stretch it 2 meters. Now, it doesn't have enough coils to actually go 3 meters, but if it did, it would stretch, it would take a force of 27 newtons. And so this ratio is always the same at 9 newtons per meter. And so that's what I mean by it's a constant, and also what I mean by it's a measure of the stiffness of the spring. How strong is that spring? How stiff is it? In other words, how much does it push back? And if that's beginning to make sense to you, you can begin to see now why the spring constant would also be in this equation and why it would be in the bottom. Now, that doesn't really explain the square root. That's going to take some calculus for that. But it does explain why it's there in the first place. And that is, you come over here to this spring, and you hook up a weight here, and you let it go, and you pull it down. I would say what is making this thing oscillate, what is bringing it back, is the stiffness of the spring. Mm-hmm. And the stiffer it is, in other words, the bigger that K number is, that Hooke's law, then the more it would pull it back. It would have more of a force that pulls it back. And so that number's got to be in there. And so a combination effect of the period would be how much stiffness does the spring have? That's represented by the spring constant K. And also by, well, what are we trying to bring back to equilibrium? How much material? How much mass? And that's why you see in this equation, even though we didn't derive it, but I still think we can get a good understanding of it, we can say that the period depends on 2 important factors. One is how much material do you have? It's inertia. And then the other one is how much you're pushing on it. How much stiffness do you have? It's spring constant. So hopefully put in that light, it's not a big surprise that you see both of them in the equation for the period of oscillation on a spring. In fact, it's also why I hung these springs, and I know on the video camera they're barely in sight here. Maybe I'll only work with 2 of them to kind of just make the time go a little bit faster. But each of these have a different stiffness to them. I also spray painted them different colors so they can, you can tell them apart. And so let me take the red one here and the white one, and maybe I'll just work with those 2 and say, all right, let me put a little bit of weight or stress on them. I already put some hangers on there, but let me add some real weight here. So how about 500 grams to each? And so I'll put a 500 grams on this red one and a 500 grams on this white one. I just out of curiosity, maybe the 2 I should do are the stiffest one and the least stiff one. And I can probably tell that. Yeah, okay, so the red and the blue aren't too much different. So I won't even bother to mess with the blue one here. But the red and the white one are the most different. In fact, maybe I'll get a color that stands out. Maybe I'll get the red marker here. And I can make maybe a little mark off to the side here and a little mark off to the side there and say, okay, that's how far they come down, and that kind of shows their stiffness, if you will. The white one being a little stiffer, right? Didn't fall down as far. But watch this. Watch what happens when I put another 500 on each of them. And so the red one stretches a little bit further down, and of course the white one stretches a little bit further down. I'll make a mark, and so here's the bottom of the red one, here's the bottom of the white one. Let me do it another time so you can see the pattern, and this is what Hooke noticed. And so if I do a third one here, and a third one here, I can have a mark down here and a mark down here. And it looks like I'll have room to just do one more, but before I go that far, are you seeing the pattern what Hooke saw? That is, it will stretch the same amount of length each time you add that additional force. See, isn't this distance from there to there looking like it's equal to the distance from there to there? See, this is how much it increased when I added 500 grams, and it did the same thing. And so this red spring increases the same amount of distance every time I put 500 on it. And you can see the same thing here, that this is the distance when that second 500 was put on it, and this is the distance when the third 500 was put on it. See, it's the same increase in distance, and so all springs have this neat property. That's why we call it Hooke's law, that they increase the same length every time you just add that same amount of force. 9, 18, 27, or in this case, 500 grams, which is about 5 newtons. So 5 newtons, 5 newtons more. So 5 newtons and 10 newtons. Well, I already had 5. So I already had 5, and so this went up to 10, and this went up to 15. Same thing here. That's already had a 5 on it when it got there, 5 newtons. And so another 5 would be maybe, well, went to here, so that's 10 newtons, and another 5 makes it 15. So it keeps increasing by that same distance. You'll see it one more time here. If I put on the last one I can fit on here. And so there's another 500. And then here is another 500. And so as I look on here, I will see then with a total of about 20 newtons, it has kept increasing the same amount. And then again, same thing here. Here I'm kind of at the bottom. Can't really write it on the whiteboard here, but it's just right here at the tray level. But I think visually, and I hope you can see this on the camera, because I know I don't have Ron to zoom in here, and it's like I got this little pole in the way. Maybe I'll just move the table, although I guess remind myself to move it back when I get on that side of it. So you could kind of see this, that it increases the same amount. And maybe I should have now erased that equation underneath it. I wanted to leave the equation there, because I still want to keep talking more about it. But this is then Hooke's law. Also in this, do you see what I'm trying to say here is I am not trying to say that all springs have the same spring constant. I'm trying to say all springs have their own unique individual spring constant. But it is a constant. It is a number that represents how stiff the spring is. So in this case, without measuring the distances here, I can't really get the spring constant, but what I could do is come over here and say this spring constant is bigger than that one. In fact, maybe I will. I've got a meter stick right here, so maybe I'll do this. What would the spring constant be for the white one, and what would the spring constant be for the red one? Because I know that each of those was an increase of roughly 5 newtons. And then each one increased by roughly, see if I can measure the white one here, that's roughly 10 centimeters and roughly 10 centimeters. So I'll go ahead and put for the white one 0.10 meters, which makes it at 50 newtons per meter for the spring constant then of the white one. Whereas the red one was roughly 20. Well, that's more of a 19. And that's more of a 19. So maybe I should call it 19 here. Although then I'll need a calculator. And so 5 divided by 0.19 comes out to be 26. I'll leave it at 26 instead of 0.3, but then newtons per meter. So again, trying to get you an idea of this spring constant and Hooke's law. So you know when you read a problem that, okay, how do I figure out the period of oscillations? I'm gonna need that. All right, well, since I only have one whiteboard to work with today, let me disassemble this so that I can see it. But I'm hoping that discussion here gave you some insight into this spring constant. And I'll clean up the equation a little bit. And so I bumped it. And so there's a 2 pi. And I'll go ahead and clear this off. But I'm hoping that gives you some gut feeling for what the spring constant is. It's the stiffness of it. And it also gives you a clue of how you're going to be calculating it on the homework problems. They'll probably describe a little bit of what happened with the spring when you put weights on it. And as you put weights on it, you know, how much did it stretch? From there, you can get its spring constant. But I also want to point out that we also know the equation then for the frequency of a spring. And so maybe to move the table so that the spring is back into the camera, if I come over here to this spring and I put this now 400 on here and let it go, oops, I could calculate its period or its frequency. And the frequency being the reciprocal then would be 1 over 2 pi. So that's what we get when we take the reciprocal of that. And then the square root of k over m. And so something that has a high frequency would then be done with something with a large spring constant or small mass. And again, maybe you could see the period and frequency if I use this horizontal one, which I think is still in the camera's view. Right now, I have really just 300 grams on here, which is this little cart right there. And I would say in this formula that the mass is really small. And because of that, I have a high frequency. And if I then dramatically increase it, because this is 1,000 grams, 1 kilogram. Now I have 1.3 kilograms. So I've increased it quite a bit. And you'll see its frequency change by a lot. You'll see that it does a lot fewer cycles in 1 second. Or in 1 minute, however you want to divide your time. Or put another way, the period. With that more mass on there, I see it's taking longer to go back and forth. In fact, I can put another 1,000 grams on this guy. Now it takes a real long time. And that's really the limit of this, but I'll go one more because I've done it in the past. It's not really designed for that. But I think it's just enough not that it doesn't rub off that bottom thing. Yeah. Well, and this is kind of bowing, yeah. So, but it's really sluggish. Really takes a long time to complete 1 cycle. So again, the frequency is low, the period is high. All right, well, maybe I've said enough then about the springs and the oscillations associated with a mass on the end of a spring. Let's get to the second big idea or big experiment in here is what about a pendulum here? Now I know I wheeled this over a little bit. Let me kind of wheel it back here and say, all right, here's this mass on the end of a string. That's referred to as a pendulum. And the period of the pendulum, again, takes a little bit of calculus. So let me just say, with the same promise, that, okay, I will work this out for you. Maybe not today, but in chapter 15 of Physics 123, we'll work this out. But I'm going to pause right there because if you see it this way, you'll begin to see that the equation for the period of a pendulum looks a lot like the equation for the period of a spring. And so, yeah, it is. It's really kind of the same physics going on. It's just instead of having the force from the spring rock it back and forth, it's gravity that is rocking it back and forth. And so probably not a surprise then that instead of having a spring constant down here, and I'm going to do something a little clever here, there would be the force of gravity. And so there's our mg. And then likewise, in the numerator, instead of having just the mass, so I'll put mass here, but this is part that is resisting it, I would probably also have the lever arm. See, because this is not really a force. This is a pivot. This is a rotation. This is a torque. And so I need to have the length of the string. And then something even quite amazingly happens for the pendulum is because the mass shows up on both the numerator and the denominator, it cancels off. And like I said, when we do this derivation, you'll see that in the derivation of it. And you end up with an equation that I think is a little surprising, and it was surprising to Galileo too, is that the period of the pendulum does not depend on the mass. It cancels off. And at first that seems surprising until you remember going all the way back to chapter 2, if I took a big mass and a small mass, and I held them out and I dropped them, what's their acceleration? And remember that discussion, that it would be 9.8. It didn't matter if one was bigger than the other. An elephant and a penny fall at the same rate. You might even remember that evacuated tube where I had a piece of metal and a piece of paper and a feather, and I evacuated it to show you that they would fall at the same rate. I even stood up here with a big softball and a little golf ball, and I dropped them, and to show you they would fall at the same rate. And later on in chapter 4, I believe it was, or maybe it was chapter 3, we explained that maybe it's not a surprise they fall at the same rate, because the one that has more mass has more weight, but it also has more inertia. And so when we talk about Newton's second law, the more weight is more force, so there's an m in the numerator, and then there's more mass, so there's an m in the denominator. They cancel off, and you get the same acceleration. And so we did that when we talked about the air friction. If you ignored the air friction, that terminal speed, if you remember that conversation, if not, go back and look at it, we were saying they would have the same acceleration regardless of how much mass they have. And so if I remember that and I come over here to the pendulum, it's like, oh yeah, that's not a big surprise. In other words, this one right here, which is about 40 grams, if I pull it to the side, gravity's pulling it back. Gravity is giving it its acceleration. And so if I take this one that, like I said, is 40, and I add a 50 and a 50 on each side, so add 100, I now have 150. But if I pull this to one side, I'm hoping you can kind of see there that this is really the same period. I should have counted it out. Oh, I did earlier. It was almost 2 seconds. And so if I did it again, it would go ready, start, 1, 1,000, 2, 1. See, it has the same period. Back when it had 40 grams, I did the same thing. Now it has 140. In fact, I'll take it apart. And I'll put 100 on each side. And so now the whole thing's up to 140. And we'll measure this much more accurately in the lab when we do it. But just kind of here in the lecture, I'll just go ready, start. 1, 1,000, 2, 1. See, it takes the same amount of time. If that's not enough mass, let me convince you with some more. And if I put 200 on each side, this thing's up to 440. And 440 is way, way bigger than the original 40. So if this thing was going to change at all with mass, you would think I would notice it by now. And I want to convince you that you won't notice it. I pull it to one side and let it go. Here we start. Ready? Start. 1, 1,000, 2, 1. Same amount of time. That's how long it takes to keep going back and forth. Has no value on the mass. Or you might say it another way, the mass cancels off. And of course, what got Galileo excited about this, and I suppose in today's world we don't think much about great inventions of the past, how important they are. You know, we can easily forget how important this really was, because this is the first time in history with Galileo's thinking that you could actually make an accurate clock. He realized then it did not matter how much mass you had on here. In other words, you don't have to be accurate. You could just simply take a string and a rock of any size. There's nothing fancy. You don't have to shave it down and get just the right. And the clock is not as accurate as you can weigh the mass. It's regardless of what mass it is. And so he would just take big rocks on the end of a string or rope and tie them up and say, this is my clock. This is how I keep time. He made many, many great discoveries because for the first time he had an accurate clock. He didn't have to use the sand in the hourglass or the water in the hourglass, or he was even using his pulse at time to try to figure out a good timing mechanism. And many of his great discoveries of mechanics came because he had an accurate clock. And so the fact that the mass doesn't depend on it was the big piece of the puzzle. But also, if you notice in here, no place in here was there the amplitude of it. In other words, what would happen if I changed the amplitude? What if I took this and I made the amplitude much smaller? Well, let me give it a try. When I get over here, I'll start it. Ready, start. 1, 1,000, 2, 1. See? Same amount of time. And you'll see that in the lab we do tomorrow. Remember, I'll say it again, we're not doing a lab today. I want you to go over the test answers instead. Tomorrow, this is what we'll do. We will do some oscillations. We will do the pendulum. You'll hear me talking about it and taking some data, and we will collect the data on this, and we will see that you can change its mass or you can change its amplitude. That does not affect the period of it. The pendulum is a simple device that only the period is changed with the length of it. Now, you might say also with the acceleration due to gravity, so if we were not on a stable platform, or if we were not on planet Earth, when we were on some other planet, then it would change. And so our pendulum clocks do need to be on a stable platform. That's one thing that Galileo learned. And actually was another interesting part of history, because that means you couldn't have an accurate timepiece on a ship sailing around the sea. That's why the British Empire offered what in today would be $1 million to anybody who could build an accurate clock out at sea. And in case you're wondering why that's relevant, is when you're out at the ocean, it's very easy to get your latitude, because you can look at the stars and you can see the angles of the stars. But it is almost impossible, and in those days was impossible, to get your longitude, because you can't look at where the stars are without also knowing what time it is. Because as the Earth goes around, the stars move, or we, of course, I guess I shouldn't say the stars move. We, of course, rotate. The stars are stationary. And so as the Earth goes around in a circle, the position of those stars and the position for is highly dependent on what time of day it is. And so the British Empire knew that if we could just get an accurate clock out at sea, then we would solve this problem of knowing where our ships are in longitude. We already know where they are in latitude. And that's why they invented the technique of selling the latitudes. They would, sail down. Maybe they'd go around South America to the, that's why they called it the Pacific Ocean, right? The calm ocean, as they sailed around South America. And they knew there was some island where they can get supplies and fresh water. They knew its latitude and its longitude was kind of questionable. Plus, they weren't even sure what their longitude was. And so they would get up to the correct latitude, and then they would sail back and forth. And sadly, there were many times where a captain would get to some spot, and so I think it's that way. Not real sure. So let's go to the east instead of the west. And they would go to the east and they'd go the wrong direction. And maybe they'd crash into a reef, or maybe they'd run out of supplies and fresh water, and then there would be mutinies. So all kinds of tragedies happen. A great book was written on it. It's called The Problem of Longitude. Great book if you've got some extra time this summer to read it. All right, but I digress. I really wanted to emphasize that Galileo's invention of the pendulum clock was one of these major discoveries, like fire in the wheel, one that we kind of overlook in the high-tech world that we live in. So notice, I'll say it again, that the period of the pendulum does not depend on its mass and does also not depend upon its amplitude. And when Galileo realized that, he realized this, that he could take a rock of any size, tie it onto a string, pull it to the side and let it go. Hours later, it may be swinging with very little amplitude, something like that, but it's still keeping the same time. And that's what he really liked about it. He goes, this could swing all day. Once I set my clock at noon or sunrise, wherever I want to, set my clock, I know for the next 24 hours, as long as it is swinging, it's going to be accurate. Now, of course, you can see there is an important piece here that determines the period of the clock of the pendulum, and that its length. And so this is the length of the string or of the pendulum. How long is that? So that's the one we have to be careful with. In fact, you can kind of see it. That's why I made the string a little bit extra in the length here. Let's see if I can unwind it here. So that if I take it here and I unloosen this clamp, maybe I'll just make it longer here at first. I'm trying to remember, the video camera, I think, went this low. And so if I pull it to one side, I claim it should have changed its period now. And so when it gets over to this side, I'll start it here and say, ready, start. 1, 1,000, 2, 1,000, 3. Yeah, and so I went all the way to over 2 seconds and just a little bit. I barely started to say 3 when it got to the other side. Or let's do the other part of this. What if I make the string shorter than I had before? And pull it to one side. And I think even on video you can begin to see, oh yeah, that's a much lower period. And I'll try to count it here. I'll go ready, start. 1, 1,000, and not even quite 1. And so, yes, very much a change here. So that's the big thing of this next little piece. I'll take the reciprocal also, because then the frequency would then look something like this. And so the period and the frequency, like I said before many times, once you know one, you also know the other. In fact, let me lower this down. I don't know how much it will get visually. I'll just take it off. I don't know if I'll even need it anymore. It will visually get in the way of the camera now that I'm kind of trapped back in here in this one whiteboard here. In fact, looking at my notes, I don't think I'm going to need the pendulum at all, so maybe I'll take this just all the way off and toss it over here on the table and say, okay, now let's go ahead and, again, keep talking about this, because here's a little fun experiment to show you. I'll maybe wheel the table back into view in case I've gotten it completely out of view. But there's another definition the author likes you to see. Let's call this then the resonance. Now, resonance, I think, is a little hard to understand, so let me see if I can demonstrate it, and I'll try it twice here. But the words I like to use here is to say it is a large increase in the vibrational, and let me use A for amplitude, when a periodic force is applied to a system at its, oh, and here's a fancy word, natural frequency. So let me start with the last word there, natural frequency. That's a word I didn't use, but it's what I was showing you. Let's come back over here to this spring. If I take this spring and I lower it back down to 100 grams, and I pull it down and I let it go, and of course I gave you the equation just a moment ago, but that equation is giving me its natural response, its natural frequency. This right here is its natural